Welcome to lecture 22, where we'll continue on the free jointed chain as a model for semi-flexible polymers before turning to the Gaussian chain as the generalization of flexible chain models. So first of all, I would like to derive with you the free energy of the freely jointed chain. And so to achieve that, we start with the ansatz that the free energy is the energy minus T times the entropy. We said for the freely jointed chain, there is no energy associated with any polymer state. So the energy is zero, and it's about how to define the entropy, and then we have access to the free energy. So we define the entropy via the enumeration of states, which I call capital omega, as a function of the number of segments and the end and distance vector. That said, although I can't really count the number of states because they're continuously distributed. But what I can do is I can use hypothetical enumeration of states to define the probability distribution. By P of N of R is equal to the number of states of N and R normalized by all states. And so why is this useful? Well, because we happen to do know the probability distribution, right? And so now taking the ln of this expression and multiplying with the Boltzmann constant, we can define the entropy as KB ln P plus KB. Okay, so S being KB. Okay, let me add one more state. So entropy is defined as KB ln the amount of states enumeration omega. And now when I move this to the left-hand side, I have an expression for the enumeration of states. And I'm going to take the ln and KB to arrive at KB ln P plus KB ln, and now this integral term. And now if we fill in the result from Tuesday on the probability distribution, we get 3/2 KB R squared over NB squared plus 3 KB ln 3 2 pi NB squared. This coming from the exponential of the Gaussian distribution, and this from the normalization factor. And then I copy down the second term here. Now, if we look at the functional form of all these three terms, we see that the end-to-end distance vector only pops up in the first term explicitly. Right? This is independent. And here, since we're integrating over all end-to-end distance vectors, it's also independent of this choice. And so this is these two terms are independent of the end-to-end distance pending and only depend on how I choose to enumerate states. But it's not important when I consider differences in entropy or the dependence on R. And so we're going to drop these, ignore. And then we directly can write down now our free energy as f of the end-to-end distance vector is, again, E minus Ts, which is minus, the minus cancels actually 3/2 kBt R squared and B squared. And I can write this as also 1/2 3 kBt and B squared R squared. Why? This should remind you of something. This should remind you of the expression for an elastic spring, right? The energy of an elastic spring, you have 1/2 the end-to-end distance of your spring, and this would constitute your your spring constant, which here I denote K, but be aware that here in this setting, this expression does not originate from the elastic energy that we store in the spring, because there is no energy associated with the system. So what we're here actually looking at is an entropic, purely entropically arising behavior that reminisces of spring. And so this is really an entropic spring constant. Entropic. And so with this in mind, we can look at, what would be for this energy, what would be the force to apply in the x direction. Say, taking the derivative of the free energy with respect to r along x, then we would get really this force extension relation with the coupling, the spring constant 3 kBt over nb squared x. If we look closely at this entropic spring constant, we see that the constant increases with temperature, which is the opposite of what we'd expect from classical solids, right? And when we here derive this linear force extension relationship, this is obviously only true in the context of our assumptions that went into the probability distribution. And so remember, for the probability distribution, to arrive at this Gaussian distribution, we assumed the number of bonds n to be large and the end-to-end distance to be bigger than the bond length. So note that the entropic spring constant increases with temperature. Conventional opposite to conventional. So let's here. And that the linear plus extension relation is only true for smaller than NB equal L, so due to Gaussian approximation. Because as R goes to L, the stretch now might explain really long. I would eventually pull on the bonds of the individual bonds. And so I would expect this force extension relationship to diverge as we approach really the full extension of the polymer. Yes, oops. It's perfectly. So we here recovered the force extension relationships based on sort of going through classical thermodynamics approach. But I find it very instructional to use this opportunity to introduce you to the block picture of polymers. And so for me, it's really a very nice example of how you can have, you can describe and essentially capture the physics of a very complex process inherently by just looking at the governing scales. And it's really a hallmark of these kind of arguments. And so not particularly no, I think the block picture is de Gennes itself, right? Oh, I'm sorry, I should have looked this up, but sort of the art of de Gennes of how to capture the physics by these simple coarse-grained arguments is what gave him the Nobel Prize. I think the block picture is one of his. It's not Flory, but it's de Gennes. So recovering, now we're going to recover the force extension with the blob, the scaling argument. Okay. So really the idea, which you hopefully learn here and you can transfer to whatever complex system in whatever physical arena you're dealing with, is transferable, is you consider here the intrinsic length and energy scales and relate them. Okay, and so what are the intrinsic scales? So the system is, we have a polymer that we're forcing apart, right? So we're applying a force on both ends of this polymer. And now this polymer, I'm just gonna draw, is like this random coiled curve that it is. And I can jump polygon on both ends. And I can decide to say that actually I only scale, I only consider the spatial scale of this polymer as on the level of, oh, I hope I changed I didn't change of blobs that are lined up in a chain. Sorry. And now, yep. And each one of them consisting as a blob. And a single of these blobs has now a size xi. And so, well, oops. Okay, so F is the pulling force extending our polymer chain. And because we're extending the polymer chain, we can sketch this chain as n over n of these blobs. Sorry, it's a little too long. Okay, so here now, this xi denotes the length scale at which the thermal energy, kBt, and the mechanical energy that we supply the system with by pulling on it, so F times xi balance. Right. So there's some thermal energy, and if I wouldn't have a force, this whole polymer could be crumbled up as a single block, a single structure. But because we're pulling on it, I'm disentangling this polymer to some extent. But how much I can disentangle by just my pulling force depends on what's the thermal force that I'm acting against that is keeping two column. And so if I just look at the balance of these two energies, that would be saying that F xi is equal or is proportional to kBt. Now, this balance of energy scales sets a length scale, namely the size of these blobs, and different forces dominate now above and below this length scale, because above this length scale, our force is the dominant energy, and below this length scale, the thermal noise, the thermal fluctuations are the dominant energy scale. So on a scale above the blobs, I have an alignment of blobs due to the pulling force. And on a scale below the blobs, they don't on the scale below, they don't experience this extension force at all, because here the thermal energy dominates. Which is crumpling up the polymer. And indeed, we can relate to how crumpled up the polymer is, right? Because the crumpling of the polymer actually on the scale of these individual blobs, this is actually given by the end-to-end distance of a polymer that only has this n amount of segments that I find in each blob, right? So n is the total amount of segments, and I divide by the blobs being all of equal length n, small n. And so here then we have the end to end distance of a single blob being psi equal to n b squared, with n number of segments in a blob. Okay, and so from that argument, I can then write down the overall end-to-end distance of my polymer. Namely, now my end-to-end distance R is n over n times the size of these blobs, right? But we know how big they are because they scale with NB, and so here we can rewrite this as NB squared over xi, with using we get this blob length scale is given by that, and from this we can get the force extension relationship. Namely, we have F is KBT over Xi from this relation up here, from the balances of energy. And now if we plug in the size of the blobs that we got from the end-to-end distance of the overall polymer, we get then KBT over NB squared end-to-end distance. And that's the correct scaling that we saw above, right? So the only difference in the functional dependence of parameters is that we have a factor of 3 popping up here in the detailed relationship, but we got all the functional dependence on the parameters of the systems correct. Why is this so powerful? So why do I really care about you appreciating the beauty of this argument? Because we had to know about the universal scaling of the end-to-end distance. This is what we put in. But otherwise, we just looked at the system and what dominates these behaviors, namely the balance of energies at the scale of disentangling the polymer with the applied force relative to the thermal energy. And this is really a powerful approach because independent of what kind of complex system you're looking at, you can, and this is here like this back of the envelope kind of argument, in the sense that this argument really fits if you just throw out the words at the back of an envelope. It's a very short argument that gives you an idea of what you would expect from a system to happen. And that's very, very powerful to have because independent of the specifics of the details, you can use this argument now to plan an experiment, right? Make sure, like, how would I choose to check out that this is going? Which are the parameters that I would like to vary to see if this relationship holds true? And also from the theoretical perspective, right? Typically, if we have any complex system and we write down the equations are always way too hard to solve analytically, right? We can't. We usually, we only teach you all these examples that we can solve, and I bet by the end of your physics studies, you've kind of seen, I would say 80% of the systems that we can exactly solve, right? But you might be lucky that you can map a system to this set of systems that we can solve, but otherwise you're stuck, and so you're always stuck, right? But what you can do is you can always take limiting cases, like send a parameter to be small to arrive at a system that you can solve, right? And so knowing ahead of time of what you would expect for your system under consideration to happen is therefore they're very, very powerful, because you can all of a sudden, you know, you have an idea of what kind of limits can I take, which ones are good ones that I'm not changing the physics. And same for numerical experiments, because always all the time you code something, you always have bugs, and I bet there's tons of codes published that still have bugs. It's the nature of things, but you have to be good at searching for them, right? And to doing sanity checks on your results. And again, these give you these sanity checks. Yeah.
Was the blob size now just a helping tool, or is there a natural way to choose it? Because you just kind of drew the circles in like in a very intuitive way. I agree, but was this arbitrary, the size of C? Because in the end it drops out. So
it drops out, but it's not arbitrary, right? It's really set, like the scale of these blobs is set by KBT over the force that I apply. So it is, there's a in a sense, what we're doing here is like we're doing a coarse graining that we know that if you're extending this, if you're pulling on the polymer, it will disentangle, and there's a coarse grained length scales at which I can draw this as again a linear chain. And so the question is, on which scale does this happen, right? And that defines the blob scale. And it may be of interest to you also to know, like, on which scale, you know, do I have these disentangled blobs, right? This is, for example, important if I'm not looking at a single polymers, but lots of polymers, and they are sort of entangled among each other, right? And I want to see now how does, like, such a whole polymer solution, how does it behave when I pull on it, right? Can I, are these, how big are these blobs? Can they actually, can a blob fit in between the mesh size of my structure so I can disentangle it, or am I acting against my entropic force on the scales as well? So the scale of the blob is something that, the size of the blob is something that does come into play in lots of other arguments.
Okay.
Okay. So after like this heuristic way of gaining physical intuition, I also want to show you that here, in this case, we can also actually calculate the force. Oops, sorry, wrong color. No, correct color. The force extension relation without any approximation. No approximation. And so that would be like going back to our statistical mechanics toolbox, where we start with a partition function. For a freely jointed chain that is set n of, and we have this force applied, and that's then summing over all states again. So sum over what? Over all states, the statistical weight of every single state that we had before. States, and now because we're applying a force, we're having an energetic contribution to the states. So we now have a Hamiltonian here of H, which depends on the configuration, with our Hamiltonian being defined as minus F R, which we can write in detail as minus summing over all segments together that set up the end-to-end distance, so FTI, which is the external pulling force. And this is now a beautiful example of how in the plethora of things that we're trying to describe as physics, we always go back to systems that we know we can solve, because there's a very small number of systems that we can actually solve. So look at the Hamiltonian. Which system does it remind you of that you already know how to solve? So we have here independent variables that are lined up, and we have an F in front of it. So I could interpret my TI as random spins, and I could interpret my F as an external applied force. And then we're back to the paramagnet. So note the analogy to a classical. This case, it's a Heisenberg paramagnet, because the spins cannot only take values 1 or plus 1 or minus 1, but the whole angle on the unit circle in an external flat field. And so since all segments TI are statistically independent, Zn so only have to care about 1 and then take it to the power of n. With my Zi of F then being just integrating over the potential states of my tangent vector, the statistical weight of each state, remember that was 4 pi b squared, the surface of the unit circle, given that my segments are bound to be of length b, and have E beta F TI here. Oh, sorry, here's a 1, so we can also just make these ones, doesn't matter. And now, so integrating over the states of my tangent means to integrate over the surface of a 3-dimensional unit sphere. And because of the constraint that the tangents all need to be of length b, so that gives me the d phi from 0 to 2 pi and minus 1 to 1 d cos theta. And with this in mind, I also write this as bf small b beta f small b cos theta. And this gives me 2 pi that cancels with the 4 pi. So and then the 2 I use because here, if I integrate this, I get eta minus beta fb minus beta plus eta minus f beta fb, and I can write this as a sine function with a prefactor kbt fb from the integration constant sine h, sorry, fb over kbt. And from this exact result of the partition function, we can then find the free energy Fn applied force is the minus kbt ln Zn minus sorry, I throw away an n minus n, kbt ln of now kbt fb sine h fb kbt. That's on purpose that you now recover material that we looked at, or like a free energy that we looked at very much previously in this class. From that, we can also again calculate the mean extension in alpha direction with our alpha as a function of applied force being defined as 1 over the partition function as normalization, summing over all states of the system again, and the weight of states. Now having our alpha here that we want to take the average over, and our Hamiltonian. And so what you can see if you write now the component of the end-to-end distance along alpha as the sum of the projection of all the tangents along the direction of alpha, we can see that this, sorry, just copying down. So this is just the sum over all I to n te alpha, ti alpha minus beta, and that was f sum over all tangents. So you see this is, you recover this by taking the derivative with respect to the force component along alpha, and that's something that we can factor out, taking this derivative. So that's the same thing as taking the derivative with respect to the force along direction of alpha of the entire partition function itself. So it's then 1 over Zn kbt ddf alpha of Zn, which is equivalent to Fn, taking directly the derivative of the free energy along this direction. And so let us choose alpha to be in parallel to the applied force. R parallel of F. Then, okay, so now we're, so here. Here's our free energy. And now we're taking derivatives with respect to F. So taking the derivative of the ln, we get a minus 1 over the whatever we have there. And kbt, okay, that's the derivative of the ln, and now we have to multiply it with the derivative of the argument of the logarithm with respect to f, which we have twice. So the first derivative then gets a minus kbt b f squared b squared, copying down the second term. Sorry, my fb kbt plus copying down the first term and taking the derivative of the second term fb, which is cos h fb over kbt and times b kbt for the inner argument. Whew. Now lots of things cancel. Let's start canceling. So first of all, I have this kbt cancel with this kbt. Then I have a 1 over like a this is actually, this is an FB, right? It's 1 over FB. So this cancels with this and this. And then, yeah, I can cancel this one with this one. I get a B left there. And what I can do now is I can, how do I see this? And then, okay, so sine H. And now, okay, now the sine H here, the sine H cancels with that one and gives me a cotange for this term. There we go. So that gives us then, so I have an N B, I'm factoring out this B here, NB, and I'm left with minus 1 over FB over KBT. The sine H cancels plus cotangents of FB over KBT. N times B is the total polymer length. And this expression that we have here is again a documented function that people had found so often that it got a name, and that's the Langevin function that goes by curly F L, and here as a function of FB over KBT. And so for this Langevin function, we know that as a function of x, it behaves as x over 3 minus x to the 3 over 45. Oops. 45 plus higher orders of x for x smaller than 1, and saturates as 1 minus 1 over x for x larger than 1. So it's something that looks like this is 1. This is plotting L of x as a function of x. So we have this potential, and then it's sort of saturating that way. So from this, we learned that for small forces, FB over KBT being small, and that's actually another argument. I'm not sure if I paid like 100% attention to this throughout this class, but you know, just to give you something that's generally true for being a good theoretical physicist. If you say something is small, it should always be something dimensionless. So then you are safe that you are not sending something to be, like if you're taking a length scale to be small, but you have to be aware if this is relative to another intrinsic length scale of the system. Because if you just have in mind that you're sending this one length scale to be 0, but you still believe that the other length scale you have in the system you can choose freely, and so make it also small, then you're not aware that your approximation might break down, right? So that's why whatever you do, you should always take care of having a dimensionless property to be small. So this really being a true statement, unit-wise in a sense too. And so when I here say for small forces, it means that the forces F are small compared to the entropic forces that we have, KBT over B. And so then in this case, if I just use this relationship, we have that then R parallel is here is x over 3, right? So that means we have times x over 3 times n times b. There we go. So we get nb squared over 3 kbt times f. And we recover the result of the Gaussian approximation. And now we also have, for stronger forces, we can calculate that too. So that would be FB over KBT being big. Then we have R parallel over L being 1 minus KBT over FB, which means that the force here goes as KBT over B as 1 over 1 minus R. So I have a functional relationship of the force relative to the end of end distance we observe, and as expected, now if I send the end of end distance to be equal to L, I get a 1 down here, 1 minus 1. So this function now diverges. The force that I need to really stretch out and unfold the entire polymer diverges, as our physical intuition would tell us. So diverges as R parallel goes to L. Okay, so I talked a long time about force extension curves, and you might have wondered why did we care. Apart from like, okay, you know, we can learn a lot of like insights of how to deal with problems on physics side, like thinking about the block picture. But it turns out that this is actually something that people can measure. And so which measurements? I think I take this one. So because what you can do is you can now put a polymer and you like, I believe these data were still done with an AFM. So you covalently bind your polymer ends to a surface and to the cantilever of your atomic force microscope, and then you can like really slowly control the force with which you pull on it, and thereby also have access to the distance that you're above the surface where your polymer is covalently bonded. So you really can measure this force extension curve. Actually, nowadays, because Matthias Rief was the person who was like, you know, he got his job for being a pro with force extension curves, and this, like, you know, not only be interested for like the context of polymer physics, but obviously then you have access to whatever is happening to these polymers as well. I recently asked him like if he still has AFMs around. Turns out no, because this is outdated. So nowadays what you do is you use optical traps. So you have then you bind covalently beads to the end of your polymers that you then control with laser lights, and you have a much more robust access to these force extension curves with this optical optische Pinzette, optical I don't know what it's called in German and in English.
Is it tweezer?
Optical tweezer. Thank you. Optical tweezer setup. So optical tweezers it is nowadays. And okay, so here's the measurement though. So this is force, this is extension curve, and look at this nice red crosses. I think you have to be really proud of yourself if these are your experiments and this is your data. Wow. Anyway, and so they nicely show like a linear behavior for small extensions and a divergence for large extensions, as we just argued. And now this is a little bit of a preempt already. So the black line is the free jointed chain, which is exactly what we calculated. So we just calculate this curve, which is nicely predicting the correct trend. But you see that there's a distinct deviation between this curve and the data. But the data actually follows other curves that may not tell you anything right now, which is the WLC, which stands for the warm light chain. So what's the difference is that the warm light chain is incorporating the stiffness of the polymer, in this case of the DNA. So there you see at small extensions, this difference doesn't show up. but at large extensions, there's regimes where this becomes the semi-flexibility becomes notable. And as a comparison, also just a simple Hooke's law that was approximating correctly our behavior for small forces and small extension is capturing that regime. And so from being able to fit now these curves to this data, we can also so we can fit here, sorry, KBT over B, and that gives us 4 piconewton nanometer over 100 nanometer. So it's a scale of 0.04 piconewton that we can infer here to govern our dynamics from this data. So yet there's a systematic quantitative difference, which is due to the finite bending stiffness of DNA. Okay, but before I'm going to take you on to the journey of looking into this bending stiffness property by looking at the Walnut chain, which is going to happen next week. I'm going to make a detour into right how we can really describe the states of polymers with the full power of theoretical physics by looking into the further simplification, namely the Gaussian chain. So the Gaussian chain is, in essence, assuming that I can describe. So in the Friedrich chain had like stiff segments of specific length b, right? And these were lined up together. And now what I'm doing is, in a sense, I'm describing these individual segments as Gaussian chains in itself. So I say like, okay, so they on average have a distance b, but this is kind of the end-to-end distance that's given by these, not Gaussian, these entropic springs that are lining up my entire polymer. So I'm doing a rescaling of the system in a sense. And it all starts with the probability. It's a reminder of the probability distribution of these entropic springs, right? Of the end-to-end distance of the freely jointed chain. Where we had P and R being, which we used in the beginning of today's class already, 2p pi n b squared over 3/4. Okay. And the reason we're gonna build a model based on this end-to-end distance was that this is a universal law that's true in the because of the central limit theorem, even if we have short-range interaction, as long as n, the number of segments, is large. So remember, true for all polymers were correlations between successive polymer segments sufficiently short-ranged and n is large. now we're gonna write the probability distribution of having n segments distributed out to an end-to-end distance of value r as a conditional probability to find the endpoint at position r, given that the starting point of the polymer is at 0. So we write this as G R N, and it's a 0 vector at 0. So conditional, this is the conditional probability for xn being at R and given, sorry, to emphasize this conditional probability, given that x0 was at 0. Or if we think about this as a conditional probability, we can also now consider this as a propagator of a random walker with of step size b, or propagator of a random walker of step size b, and then n would correspond to the time of the random walker. So again, everything is always the same. Everything that you see in classes is always the same. There's just a limited set. And so this reinterpretation of what we actually had, found as results before now allows us to write down a path integral, a representation of the Gaussian chain. So the drawing being that I consider now, if this is, I write this as R0, R1, R2, N, and all of these are random Gaussian chains. With this being a so-called Gaussian subpolymer. So we dissect a polymer into I want to here capital N subpolymers with a large number of segments each. So we can derive it with this, we can describe it with the universal law for the probability distribution of the end-to-end distances, so that we know that the mean squared end-to-end distance of each subpolymer is I don't know, with capital delta n b squared, and of the entire polymer I then have this capital R as n b squared, which is m delta squared, with n equal m times n. And so here, as in the drawing, I now denote as Ri the initial positions of each subpolymer. With G Rn. Now, being able to write down our conditional probability, which we're gonna identify as our propagator, the Green's function, as integration over m minus 1 dri 3 over 2 pi delta squared, counting all the individual, you're writing down all the individual end-to-end distances of the individual chains making up the system, where the end-to-end distance is given by m ri minus 1 squared for each individual, and then I count overall. So this is the total polymer that I have here on the left-hand side, and on the right-hand side, this is the discrete enumeration of all the polymers, and now all the subpolymers. And now what I can do is I can take the limit of sending delta to 0 and at the same time m to infinity, so making my reducing the scale of my initial of my subpolymers, and then this integral becomes a functional integral over the curve of the backbone, say, of the polymer. And we need to take this detour of describing the polymer as a chain of Gaussian polymers, because otherwise we wouldn't be able to take this limit of setting delta to 0, right? So now take limit delta to 0 to reach continuum. Which would be not defined or discrete. Just to mention, in the random walker picture, this what we're doing here would correspond to the Wiener process. Okay, and I take now, but I take the continuum limit such that I send m to infinity and delta to 0, such that m times delta squared, so the end-to-end distance squared, which corresponds to a previous nv squared, is finite. That then defines our right now still called conditional probability to be a path integral of the chain denoted starting by 0 and going up to the position at n, which is given by r, of a functional and here the delta then becomes 2 r 0 d sigma dr over d sigma squared, with sigma defined as I over m in 0 and 1, a continuous variable. And so I hope we now mapped again polymer statistics on into a description that is familiar to you, namely a path integral description that now enumerates the number of states of a flexible polymer. So this is the path integral formulation of the Gaussian chain. And so the solution we know from before. We know that G of R, and sorry, now this doesn't depend on N anymore, but actually on sigma, sorry. Sigma, that I sent to be 1. And so here, this is R of sigma equal 1. That makes sense. R1 given 0 at 0. This is, again, the Gaussian. Ah, sorry, not here. And similarly, I can now also access all positions along this polymer state. So for an arbitrary sigma, this would then be going from 0, 0 to sigma. Now at sigma being R, functional integral. Integrating over up to sigma, where now I use mu as a new variable to describe the derivative here, which is then solved by the sigma popping up as a sorry, there's a 2 missing. Note that this, again, as we've seen it before, is that the solution to the diffusion equation. Equation, whereas we have d sigma of G of R sigma 0, 1 is given by with now this being the sorry. This being the diffusivity. And so we can interpret now our probability distribution, probability as the propagator of the Green's function solving these this diffusion equation. Thus, the propagator, i.e. the Green's function, is again this path integral. Just copying. well, sorry. There was a difference. So that's the I wanted to write it down in a general form. So from R to R prime, tau, tau, R prime. And then we go here from tau to sigma, d mu, dr, d mu squared. Okay. So this was a little mathy, but I wanted to show you to you because what we did here was we changed the microscopic behavior of the model, namely replacing the rigid bonds by Gaussian change, but the macroscopic dynamics stay the same. And this is, in a way, reminisces you of the renormalization. That we here have a system where we change, if you change the microscopic dynamic, it doesn't affect the microscopic behavior. So to have this red line of thought of how we can think about statistical systems popping up here again. The Gaussian chain. But macroscopic. And there's an alternative interpretation. That what we're doing here is a coarse graining of the molecular length scale. So from segment B, we coarse grain into an entropic spring of length scale delta and stiffness K entropic as 3 kBt delta squared. And we go from the bead rod picture to a bead spring picture. The segments being represented by rods. And then the end-to-end distribution of the unit here was B, whereas here the end-to-end distribution of a unit, of the unit which here is the spring now, is delta squared, which is NB squared, and the corresponding propagator. Another feature of the Gaussian chain is that I can actually interpret this integral of propagator as a function integral over an effective Hamiltonian, which has a name. It's called the Edwards Hamiltonian. So the Gaussian chain integral formulation can be rewritten as G of R sigma equal 1 starting from 0, 0 as 0, 0. And now interpreting this as an effective Hamiltonian. But this is the sum over all polymer states or paths are sigma. And the Edwards Hamiltonian is then denoted by epsilon over 2 integral over the contour of the polymer d sigma d r sigma, and where we here have once this epsilon we can read off to be 3 kBt over r squared, which is in this context our entropic line tension of a bended curve path, and this is our effective coarse-grained free energy. Note that this Hamiltonian is we can interpret this as a Hamiltonian, but it's not a microscopic Hamiltonian. It's describing the statistics of the polymer curves, but it's not arising from it's not a microscopic Hamiltonian because it if we send the temperature of the system to 0, it would vanish. So not so vanishes as t goes to 0. But within this framework, we can then from that on calculate any expectation values as we're used to from thermodynamics, integrating then over this curves and taking care of this effective Hamiltonian that depends on the. Okay, so this just is a detour that you can the plethora of how you can map systems onto each other and then thereby use toolboxes of how to solve system that you've seen in other contexts. Yet in the end, how do we typically verify our theoretical results? I showed one example of like the force extension curve, another which that's already very advanced experiments that only became available about 25 years ago. And previously, or like the normal way of how we want to learn about the structure of matter is to do scattering experiments. So as a last journey in the context of flexible polymers, before we start semi-flexible polymers, I will talk about, or we will derive the scattering results, or at least I will start with it. Let's put it that way. There's no way I can finish. So as an experimental observation, the standard method is to look at scattering. Remember, we did this for the Ginzburg-Landau theory 2. Here now, in the context of we're going back to the freely jointed chain, leaving the Gaussian chain formulation. Experimentally available is the scattering function, which is defined as SQ being the Fourier transform of the density. Sorry, that's between the density. No, C, that's Q squared. So with rho of Q, the Fourier transform of the density. And we for free get the average. So how do we define the Fourier transform of the density? Well, via Fourier transform, eta minus, I all the way, IQ R with a rho over R. And the density of our freely jointed chain is just following all the beats that we have located at, and now here I'm actually using the capital R to denote the beats position. Again, summing over beats at Ri. And so like if you plug in this sum of our delta functions in here, this becomes a sum over the positions of the speeds. We have rho of Q, the sum over the position of all beats, IQ, I. And so now the scattering function is the square of this. So is then the expectation value of I Q Ri minus Rg. There we go. This is we know that the this is a Gaussian variable. So this rewrites as the sum of because it's a Gaussian variable, I can move the average into the exponential function, rendering it at minus a half Q alpha Q beta. Now looking at the average of R I alpha minus R J alpha R I beta minus R J beta, denoting the Cartesian coordinates. Stop. Okay, so we need to evaluate this expression for the freely jointed chain. So we know, so with alpha and beta, this is denoting the different Cartesian coordinates direction. And by rotational symmetry, we know that the different Cartesian coordinates are uncorrelated. So by they're uncorrelated, so that means that this is delta alpha beta, and now I only have to look at the average of Ri minus Rj squared. And that we can write as the sum over the distances between summing up all the segments in between index I and j, right? Was I go from k equal I plus 1 to k equal j. This gives me the distance, and then I have to square it. So where this rk is rk minus 1. And then I can pull out the sums. K bar. So that's then looking at the correlations of the distance vectors, so tensions, and we know that these are just equal to if k and k bar are the same. So this gives me a delta alpha beta sum from k equal I plus 1 to j over b squared. And so this gives then the prefactor, this is delta alpha beta b squared j minus I. So just the spatial distance between them. And so now returning to the scattering function. We can then write down the scattering function as the sum over half q squared b squared j minus I. Okay, and this is where we're going to continue on Tuesday to interpret this result. I hope the calculation reminded you of our calculations that we did for using also Gaussian variables when we looked at the Landau-Ginzburg. And so this is to show you that, you know, in the end, like all the methods that you see, they happen to come up again, because there's just a certain amount of methods that you can use in the end. Okay, that's the end of today, and I would love to thank you for your attention.